Hello, I'm Parzianello from the University of Notre Dame, and I'll present our work on Saliency-Guided Textured Contact Lens-Aware Iris Recognition. So we've been working on the iris recognition problem with limited information, or more specifically, we want to perform the recognition when the unidentified subject is wearing a textured contact lens. In order to do that, we take advantage of how these cosmetic or textured contact lenses are built. Even though they cover almost the entire iris, for some of the region around the pupil, it often remains uncovered because of this opening in the middle that allows light to go through and also accounts for pupil dilation. So, therefore, our idea is to use this authentic information for matches. So, with our goal to determine whether an image of a subject wearing a textured contact lens, which is the probe in this picture, is or not a match to an enrolled or live image that we know of that is enrolled in a database, we can see the contact lens pattern on the right hand side that is affecting the iris pattern and the authentic iris texture annotated in the green region. Now, as you can see, this is not an ideal scenario for an iris matching. The recommended percentage of visible iris by international standards is 70% or above, and these two curves show how much iris texture we actually observe in our example dataset. Most images don't even reach 15% of iris texture that is usable for a match, while almost no sample goes beyond half of the recommended 70%. Our solution for this recognition problem can be divided into two sub-problems, which are solved by distinct models, a segmenter and a matcher. First one is this textured contact lens aware segmenter, which is the deep learning model based on MASCAR CNN that is fine-tuned on human annotated data to segment the context from the iris texture itself, just like that green area I showed you before. We use a subset of the Notre Dame photometric stereo iris dataset, which has over 5,700 images, out of which 1,171 are images of irises wearing a textured contact lens that were annotated so that the original iris texture is separated from the contact lens texture itself. Using this data, we fine-tuned a mask RCNM model to perform this finer segmentation in order to pass the resulting mask to the TCLA matcher later. This is an evaluation of the TCLA segmenter on data that was left out when training our model. It shows an intersection over union above 0.5 on nearly 3/4 of the images, with a significant part of the set with an IOU above 0.9. So the second part is our proposed TCLA matcher, which is the model that actually performs the matcher after the segmentation is done. The TCLA matcher is a Siamese neural network model that returns the distance of a given pair of irises. The probe irises have the regions of interest predicted by the TCLA segmenter, while our regular segmenter is applied on the enrolled images. Like other Siamese networks, this also shares the weights and biases between the two inputs, so that when they're training, the loss is calculated for a pair of inputs, like in a contrastive loss. In our experiments, however, we obtained better results using a triplet loss instead, by computing it from 3 images, an anchor, a positive, and a negative sample. The anchor would be the enrolled image, a positive would be the genuine counterpart, and a negative would be the imposter counterpart. Moreover, the TCLA matcher uses ResNet 18 as a backbone, and it outputs a real number that represents the Euclidean distance between the embedding representations of the inputs. This matching distance can be later thresholded to obtain a binary decision. As a preprocessing step, we either normalize or crop the images before they are fed into the network. With the rubber sheet normalization, there is no information about the periocular region. With the cropped or the iris-centric normalization, most of the periocular region is removed and only part of the sclera and the surroundings is preserved. Saliency guidance. So, besides normalizing or cropping the images, we also investigated the effects of two kinds of saliency guidance. The first one is Gaussian blur, and the second, the random noise. The idea behind the usage of spatial saliency guidance by our proposed segmenter is to guide the training process of the Siamese network towards regions containing unoccluded iris. We don't want to use binary masks, as they create strong image gradients, which could result in fake features that are not related to a given identity. So instead, we examine two approaches. The first removes high-frequency information from non-salient regions by blurring them, and the other one replaces non-salient regions with random noise, which we hope should discourage the network from using these noisy image areas. By doing that, the Siamese network is coached during the training on which regions of the iris that is covered by a textured contact lens are worth using in feature extraction. We compared each combination of normalization and saliency guidance to determine the effects of each change in the final distributions. These experiments were trained on randomly sampled images to form a train and a validation set, and these numbers are the sensitivity indices, or D' values, which is a measure of distance between two normal distributions of different means and standard deviations. In our case, every time we refer to D', we're measuring the difference between a genuine and an imposter distribution of pairs. The greater this value is, the better the classifier in question is. These D' values were obtained from their respective validation sets, while the testing set is left out for the final comparison against the baseline matcher. Each cell in this table summarizes the average of 5 independent executions with one standard deviation in parentheses. In the first column, we have a control group that does not use any saliency. It takes the images raw as they are, only with the proper normalization in question. These empirical results show that the preprocessing method that combines Gaussian blur saliency with iris normalization performed better than others, and that replacing the contact lens texture with random noise seems to be harmful for the learning process. To evaluate our TCLA matcher, we need to obtain a baseline performance. Since we could not find any matcher specifically designed for the problem of subjects wearing texture contact lenses, we used the then state-of-the-art iris recognition method, which is BSIF-based, meaning it uses binarized statistical image features and computes the Hamming distance of the iris codes derived from the images. For our problem, these iris codes were masked using the masks predicted by the TCLA segmenter in order to discard the information on the textured contact lenses themselves. By using the same segmentation masks for both methods, we also separate the two problems for a fair evaluation of only the matchers themselves. This BSIF matcher uses a set of filters that can change in number and size. Therefore, to make a fair comparison, we analyze the best combination for the task. This is the table showing the fitness as the sensitivity index of each set of filters on the data for matches using the new annotated masks. Under normal circumstances, it's not uncommon to find a sensitivity index above 6 for this method. Yet here, we see the most suited filter sets achieve a D' around 0.7, 0.76. So none of them appears to be a reliable matcher for this problem, despite being state-of-the-art in regular matching. For our baseline comparison, we chose the best filter set from the previous slide and plotted the distributions of genuine and imposter matches. These two curves indicate probe irises when they are compared against the second enrolled iris. In blue, we have genuine pairs, and in magenta, we have imposter pairs. Ideally, in a good matcher, we want to see these two curves well separated and without any overlap, which correlates with a high sensitivity index. On the left, we have the curves for the BSIF matcher with the best filter set selected for this task. On the right, our TCLA matcher using blur as saliency along with normalization, which is the best scenario in that previous table. The TCLA matcher outperforms the BSIF method with a D' almost 3 times greater and a reduction of the equal error rate from 33% to under 11%. While not perfect, it's worth remembering that many samples have less than 15% of the iris visible, that is, unaffected by the contact lens. So this represents a significant improvement on the iris recognition under these circumstances. So here are the takeaways of this paper. First, we show that the textured contact lens-aware iris recognition is possible at a lower confidence rate, but still much better than chance and better than state-of-the-art method that assumes a live iris, even when this method is paired with a contact lens-aware segmentation. Second, the saliency-guided version using Gaussian blur performed better than no saliency and random noise to replace regions to be ignored. This indicates that the training process can be guided in a way that increases both the accuracy and the human interpretability of the solution. Finally, the models generated and the dataset annotations are publicly available at this GitHub location. Thank you for your attention.